I'm going to do two examples of acid dissociation and use benzoic acid for both of the examples. So a dissociation is when you're taking the acid or base and water and it's finding its equilibrium between its conjugate acid and base pairs. If you don't remember, a conjugate acid-base pair would be, for this example, the benzoic acid is donating its hydrogen to the water to create hydronium, and its conjugate ion would be its pair. This is the acid and its conjugate base. Whereas water can be an acid or a base, and in this case it's acting as the base accepting the hydrogen. So you would say water here is the base, and the hydronium is the conjugate acid. So in this equation, this first example, you're given that the Ka of benzoic acid is 6.30 times 10 to the negative 5. And that you have a 0.0074 molar solution. So our initial, we're going to do our ice chart here, is 0.00743 moles per liter. In this equation, you're asked to find the pH. We can find the pH if we know the concentration of the hydronium ion. So we are going to set up our ice chart knowing that none of our conjugate acid or conjugate base exist initially, and that water is the solvent in this equation. You don't have a concentration, so there is no variable change for the concentration of water. We just have one of the reactants. Minus X for the acid, plus X for both conjugates, and you get your formula that you can plug in to your Ka expression. Now a Ka or Kb expression is just an equilibrium expression for a particular acid or base. Ka just means the equilibrium constant for that acid. So we have our products, both being X, so I'm going to write it as X squared, over our reactant 0.00743 minus X. Now, in this question, we're going to have to do the quadratic formula, knowing that 6.300 is the Ka. We can plug it in, multiply 6.300. I'll do it in two steps for you. So we have 6.30 times 10 to the negative 5 times 0.00743 minus X equals X squared. Rearrange that and you have 0 equals X squared. It's going to be plus 6.30 times 10 to the negative 5x, and then 6.3 times 0.00743 and brought over to the other side will be minus 4.6809 times 10 to the negative 7. We're going to plug that into the quadratic formula. I'm sure you can do that. And you're going to get that X equals 6.53395 times 10 to the negative 4, or X equals negative 7.1639 times 10 to the negative 4. Now, this second answer is negative and thus impossible. You can't subtract a negative and thus add benzoic acid out of nowhere. So this is our concentration of both the conjugate base and conjugate acid. Knowing that the pH equals negative log of the concentration of H3O plus, and the concentration of H3O plus is 6.53395 times 10 to the negative 4, you can do negative log of that value, 3395 times 10 to the negative 4, to get your pH. Plug that in, and and you're going to get the final answer that the pH is 3.1848. Just going to write it in the center here because I ran out of space. pH equals 1848, which is 3.18 to the proper significant figure. Okay, in our second example here, we're given the same benzoic acid and an initial concentration, and again asked to find the pH. One note before we get that, benzoic acid is monoprotic, meaning it'll only donate one of its hydrogens. If you see this and don't want to write out the whole equation each time, writing the general equation like this for any acid-base dissociation will tell you everything you need to know. Your monoprotic acid has one hydrogen. It's an acid, so it donates this hydrogen to the water to get your hydronium. You're left with a negative ion of your conjugate acid, conjugate base of this acid, and hydronium. And that will work for any monoprotic acid. So if you're lazy and you don't want to write benzoic acid in your ice chart every time, that is fine. Okay, so for this question, you're given an initial concentration of 0.15 moles per liter. Again, water, nothing, and you have none of your conjugates to start with. Minus x plus x plus x for the change, and you have a very straightforward Ka expression. I'm going to write you out that you again know the Ka is 6.3 times 10 to the negative 5, and your expression here is that value is equal to x squared over 0.15 minus x. Now, in this example, you can do something to avoid having to do the quadratic formula. This change in x can be neglected when your initial concentration and your Ka value are more than 3 magnitude greater than each other. So here you have a concentration times 10 to the negative 1 and a Ka times 10 to the negative 5. Meaning this x will change very minimally, so that when you subtract it, you're subtracting the 4th or 5th or 6th significant figure. Ultimately, when you round this to 2, you won't change that number. So you can neglect this change in x for this question and jump right to multiplying 0.15 times your Ka value and taking the square root instead of having to do the quadratic formula. So your x value will look like the square root of 6.3 times 10 to the negative 5 times 0.15. That's a much simpler calculation. You get that value is 3.0741 times 10 to the negative 3. And you're asked for pH in this equation, so do the negative log of the concentration of H3O plus, which is the negative log of x, which is 3.0741 times 10 to the negative 3, and you get that your pH is 2.51228, which is 2.5 when rounded to the proper significant figure.